All right, last one of curve sketching. This one's a radical function because, it's got a radical in it. So we're just going to go through. We're going to figure out each of these things and sketch the graph. All right, so domain restrictions. Remember, we have domain restrictions anytime we do anything that's illegal in math. And the two things that are illegal is we can't divide by 0 and we can't take the square root of a negative number. So we look at this one and we say, okay, are there any domain restrictions? Well, for it to be dividing by 0, we need to, the denominator, square root x squared plus 2, would have to equal 0. So if we square both sides, we have x squared plus 2 equals 0. We subtract 2 from both sides, we have x squared equals negative 2. Are there any numbers in the real number system that when you square them, they become negative 2? Nope, there's really nothing. You can't take the square root of negative 2, at least with real numbers. So this one has a domain, or this denominator can never be equal to 0. In fact, it can never even be negative. We can never have a negative number in there because there's not a single number out there that if you put it in for x and then add 2 to it, it's going to be negative. So our domain for this one is all reals. Our vertical asymptotes, well, if our domain is all reals, we have no vertical asymptotes and we have no holes. Our x-intercept is going to be when y is equal to 0, and so that's when our numerator is equal to 0. And our numerator is x, which means that it is going to be, oops, I just pushed a button, and now it won't let me do it. Okay. There we go. Back. I'm back. See if there we go. Okay. So our x-intercept is at 0, 0. Our y-intercept is when x equals 0. When x equals 0, y also equals 0. So our x-intercept or y-intercept is also 0, 0. Our end behavior is the limit as x approaches negative infinity of f of x, and the limit as x approaches infinity of f of x. Well, when we get to a negative number, now remember, this is what this looks like. Basically, this is like x over absolute value of x, right? Because the square root of x squared is the absolute value of x. It's just basically the positive version of x. So if I put a hugely negative number in here, I get a hugely negative number over a hugely positive number, so it's going to be negative 1. And if I put a hugely positive number, I get a huge positive over a huge positive, which is positive 1. So that means we're going to have horizontal asymptotes at positive 1 and negative 1. And our symmetry, if we put in, I'm going to rewrite that. Our symmetry, all right. If we put in 1 into this, I have 1 over root 3. And if I put negative 1, I have negative 1 over root 3. So that's going to have origin symmetry, because if I put in 1, I get out 1 over root 3. And if I put in negative 1, I get a negative 1 over root 3. So that is origin symmetry. Now we're going to get into the calculus. So relative max would be, we got to find our critical numbers first. So our critical numbers are when the derivative is either equal to 0 or undefined. So when would this be equal to 0? Well, that would be when the numerator is equal to 0, and the numerator is never equal to 0 on this one. So it's never equal to 0. But it might be undefined because the denominator, nope, nope, there's no critical numbers because the denominator can never equal 0 either. So the derivative of this is never 0. It's never undefined. So there are none. So there are no critical numbers, which means there's automatically no mins or maxes. So let's see, though. Let's draw an f prime number line and just see what's happening, because what's going on with this function, right? There's no critical number, so it's never going to change. Let's find out if it's increasing or if it's decreasing. So the derivative, let's put in 0 because it's easy. So we go, it would be 2 over 2 cubed, and then the square root of that. So it's positive over positive, so it's always positive. So the derivative is positive, which means this is always increasing. And then we're going to look for our possible inflection points, our pips. And those are going to be when the second derivative is equal to 0 or undefined. And in this case, our second derivative could be 0. When x equals 0, our second derivative is equal to 0. And then undefined, that can never be equal to 0 because we can never divide by 0 because there's not a number that when you square it and add 2 that it's ever going to be 0. There's also not a number that when you square it and add 2 that it's ever going to be negative, so we're not going to ever be taking the square root of a negative number. So our only possible inflection point is 0. So we're going to make an f double prime number line. And our possible inflection point is 0, so then we see what's going on with our second derivative. Is it concave up, concave down? So at -1, if we put -1 into our function, we get -6 times -1, which is going to be positive. And then on the bottom, it's also going to be positive. So it's positive on before 0. And then after 0, if we put in +1, we get out negative and positive. So it's going to be negative here. So it goes from being concave up to concave down. So our point of inflection is at 0 and 0, because when I plug 0 into the original equation, it comes out 0. So now let's graph it. Get some red in here. All right. So our domain is all reals. We don't have any vertical asymptotes. We don't have any holes. We have an x-intercept at 0, 0. A y-intercept at 0, 0. We have this horizontal asymptote at -1. And a vertical asymptote, or a horizontal asymptote at 1. Now notice that I didn't draw them all the way through, because what's happening is when x is getting closer and closer to negative infinity, it's approaching -1. And when x is getting closer to positive infinity, it's approaching +1. So, like on this side of the equation, or on this side of the graph, it's getting closer to negative infinity. So it wouldn't be approaching 1 on that side. It'd only be approaching 1 as it's going to positive infinity. We don't have any relative max or relative min, which makes sense because it's approaching an asymptote, so it just keeps getting bigger and bigger and bigger, like closer. And our inflection point is at 0, 0, 0. And so we know that it's concave down here, because it's approaching that asymptote, and then it's concave up here. And that's it. That's that whole curve.